Okay, 2A. Um, I'm going to do this two different ways. It turns out there's an easy way to do it because of the numbers they give you, and that's how they showed it. But then I'm going to show you the way that we did this when I taught it. Okay. Um, I actually showed you both ways, but I told you this. This is funny. I told you that this way wouldn't be there, but it showed up last year. So in last year's test, what we know is the velocity was 55 here and 55 here. Well, if the velocity is 55, that means the average rate of change, the average rate of change of the velocity was 0. Didn't change. The average. Remember, we have something called the mean value theorem. Says if the average is 0, then that must mean that the derivative has to be 0. The key to this question, of course, is acceleration is the derivative of velocity. So the acceleration has to be equal to f of 2.8. I'm going to just write it out. F of 0.3 all over 2.8 minus 0.3. Well, that's not 0.5, 0.3. So it's at 55 minus 55 over 2.5, which is 0. Now, as we talked about before, I don't know, I didn't actually expect them to do these because it's a little convoluted, right? Because it only works because these both happen to be 55. But that's it, that's it. What do we know? The derivative has to equal the average slope somewhere. If the average slope is 0, and this is actually a subset of the mean value theorem called Rolle's theorem. But anyway, so if the average slope is 0, then somewhere, there's no way that I can have 2 points like this and not draw it as long as it's differentiable so that the derivative was 0 at least once, right? So now, what would you do if, like, I just want to point out, what if this was 54? Okay, instead of 55. Here's what you do. You would say, well, to go from, you could say the velocity increases when on the interval 0.3 t, no, decreases, sorry, my fault. The velocity is decreasing between 0.3 and 1.7, because it goes from 55 to 120. We could actually calculate that number like we did here, but what you want to kind of point out is that the acceleration, the derivative, if I actually found that slope here, between here and here, don't actually calculate it. Don't actually, just say the acceleration is negative on the interval for some t, for some t. Since the velocity went from 55 to negative 129, the average rate of change, or what we say the average acceleration is less than 0. That doesn't mean that it's always less than 0, but for at least one value of t, the acceleration would have to be negative. On the other hand, I go from negative 29 up to 55, same thing. The acceleration would have to be positive on the interval 1.7 t to 2.8 for some t. Now, you could do this and do the calculation. All that I actually care, though, is the acceleration was negative at least 1 for some value on that interval. It was at least negative on that, and then the acceleration was positive for some t on this interval. And then by the intermediate value theorem, you can't go from, we know that the acceleration would have to be 0 somewhere on the interval 0.3 t to 2.8. So at least once. We're not saying acceleration is always positive. We know the acceleration goes from 50, sorry, negative. Again, let me just say this again. The velocity went from 55 to negative 29. So the average acceleration, which is the derivative velocity, would be negative. So that number would be negative. That doesn't mean this is always negative, but it's got to be negative at least once. And then you can't go from negative 29 up to 55 without, that's got a positive slope. So the average rate is positive, which means the derivative has to be positive at least once. So you can't go from a negative to a positive without passing through zero if it's a continuous function, at least once. Now, again, this is a much easier way to do it, but I do want to point out that it's really easy to do because of the 55s both being 55 and you get the zero. So be aware of that.